This is not an atypical looking problem. It's a Faraday's Law question, and the focus of a question like this is threefold. First, the question is going to have something on the order of the magnetic field is going to have a change, and it could be any number of things. I've seen something as simple as they give values for the magnetic field and tell you how long it's changing, or something as ridiculous as like they give CT squared plus BT or something like that, some expression for the magnetic field and how it's changing over time. And we'll leave this one here because I want to try and combine three things into this real quick example. The first thing they'll do is they'll tell you that you have a resistor or a light bulb in the circuit. And it's not uncommon for them to have more than one in a single loop like this. And sometimes they'll even have a secondary loop someplace else with something else in that loop. The important part is that focus on your loop and focus on where the magnetic field is. They're throwing distracting information out here for a reason. So they'll ask a question like, what is the current magnetic flux? This one would be pretty straightforward. And they'll say, at a specific instance in time, derive an expression for the magnetic flux. What they are looking for you to do is to make a stupid mistake here. And I'm not sure you'll make this mistake or not. So I'm going to give you guys a moment. Can you just scribble out what you think the expression for the magnetic flux will look like based on what's pictured right here? And I'm looking for a specific mistake. It won't matter, but yes, we're assuming that this is the expression for the magnetic field. So you should not have a capital B in your answer. Okay. I'm making sure everybody else got it. I believe in you.
No, I just have you're listening.
I've made it a personal rule. So the biggest thing to look at here is flux refers to only the portion of the area where there is a magnetic field. So when you're working this out, we could say the B was a constant, so we can put our CT squared plus BT as the magnetic field, and we need to sum up the entire area. I think we can all agree that's cosine of 0 degrees. So now we're just looking at the area. The crux here, where we see the first kind of silly mistake, is understanding that this should be pi r2 squared to indicate the entire loop. No, that's a lie. You weren't even hearing. I said it has to be only the place where the magnetic field exists. So flux only refers to the portion of the area where there is a magnetic field. It does not refer to the entire area of the loop. A lot of students will make that as a silly mistake, but let's understand that that's on like 50% of the Faraday's Law questions that involve a changing magnetic field or something like that. Yes, sir?
Isn't the magnetic field changing? Why is it being brought out?
The magnetic field is changing with actually, that's a good question. And I've never really addressed it probably fully. And let's be really clear about it. This integral is not with respect to time. This integral is is an integral based on area. We are looking at a momentary amount of flux at a specific instant in time. So it's not related to time as it changes. So at any moment, we could plug in whatever value for time we want and get what the flux is. So a flux is a calculation. Now, there might be no magnetic field there. We don't know. And should you put in 0 for t, you would find there'd be no flux. But we're not actually asking for what the flux is at a single point in time. We're looking for an expression for the flux. This is an expression for the flux, which just adds up how much magnetic field passes through an area. Now, Faraday's law will care about the fact that the magnetic field is changing. So the next portion will be for you to conduct Faraday's law. Again, I don't think that's a big deal, but it's likely in a problem like this, you're going to get some kind of expression for the magnetic field that has to do with time. So your next job is to recognize the number of loops you have and to come up with an expression for the magnetic field. I'm sorry, an expression for the EMF. Not particularly hard. I'll give you guys a moment to do that. All right, so you should be done by now. The pi r1 squared isn't changing with respect to time. There is a single loop. So in conducting the EMF, I will have minus pi r1 squared, and then we'll have the derivative with respect to time of ct squared plus bt. And that should be pretty straightforward. Can't help that. Now, part 3 generally will have, or the next thing that they'll generally ask is, we have a clear circuit here, and they give a resistance. So they will likely ask, what is an expression for the current passing through the resistor, and draw an arrow to indicate the direction of that current. So to do that, I've specified that both C and B are positive constants, which I think you need to have in order to be able to calculate that. Now, the current part, not interesting. Just one more and a large number of R's that you have to keep track of all the time. The direction part might be interesting. Now, you had to draw an arrow either to the left or to the right to indicate the direction of the current that is currently being developed in that resistor. So point. Left if you think it goes left, or right if you think it goes right. Yep. Now, the current in this circuit has to try and oppose the change in the magnetic flux. The magnetic flux is increasing into the board, right? Because it's an increasing function. It's linear. So it's increasing into the board. So we need an increasing out of the board flux to counter the change in flux that we have. So I just use the curl rule to try and say, well, it's going to be out of the board or into the board. It's going to be out of the board. Move it around up here, so current should be going that way, counterclockwise through the loop. Now, this might not be clear to you, but bless you.
So the reason why it's going semiconductors is because you want the magnetic field that this current produces going against the magnetic field.
I'm not going to use the word want. the direction of the current is to oppose the change in the magnetic flux. There's a magnetic flux that is currently into the board, and it's getting greater into the board. To oppose that, the current that's being created has to generate its own magnetic field that is out of the board. I don't know if I have their hand up over here, but go ahead.
So if it was decreasing, it would be going the opposite direction?
Yeah. Yeah. So I and just so you guys know, I had to specify this in order for us to be able to make that decision. If I hadn't specified that, if one of those constants was negative, don't know. And there's a point of inflection too, potentially. But remember that the magnetic field is a growing function like it is here. Then the current that's going to have to be created has to try and oppose that change in magnetic field. At point P, is there a magnetic field? And if so, is it into or out of the board? At point P, is there a magnetic field? And if so, is it into or out of the board? So does everybody understand why I'm asking this question? There is an external magnetic field. And that external magnetic field is what is creating the current, because that magnetic field is changing. Interestingly enough, the loop is now generating its own magnetic field, and that magnetic field is out of the board. And that magnetic field will exist everywhere in this loop. Not the same strength everywhere in the loop, but will exist everywhere in this loop. We are going to have to deal with the fact that this current is generating a magnetic field, and this magnetic field penetrates the area of its own loop. I want you to hear this because we have something next week that we have to talk about that's actually hard. This stuff isn't the hard stuff. That's why I have to nail this. There is something called self-inductance. We have been ignoring this the entire unit, the entire year. It's something that has been happening in all of our circuits. Any circuit with a current is a closed loop with a current. By definition, all circuits are loops. And once we have a closed loop and generate a current, we have generated a magnetic field. That magnetic field has been through a closed loop and therefore creates an induced current in itself. So this magnetic field, the red dots, is created the moment the magnetic field starts to change. So all circuits have what's known as self-inductance. And I want you to hear this very carefully because it's going to be a big deal next week. Self-inductance is something that tries to restrict the establishment of a current. I don't want to use the word resist because there's resistors. It tries to restrict the establishment of a current. It also tries to restrict you taking away that current. I probably could say changes in current. That probably would be better. I tried to say it in more clear terms, but changes would work just fine. So anytime you try to turn on a current or anytime you try to turn off a current, there is the creation of a magnetic field that tries to prevent that change. And this is called self-inductance. So all of those sparks you've ever seen when you've tried to connect something to a battery or disconnect something from a battery is, believe it or not, more caused by self-inductance than anything else. When you try to pull that wire away from the battery, self-inductance is such a strong presence in your circuit, it tries to continue that current even under the circumstances where there's no connected power anymore. So much so it will push the electrons across the gap. We've said it's because it's a really high electric field, but almost always it occurs because of this self-inductance property. Most of the sparks we see tend to come from there. Yes?
So for for R1, would that mean that there is no magnetic field there, or there are two magnetic fields in the opposite direction?
There's likely there won't be two magnetic fields in opposite directions. Magnetic fields, like electric fields, add together and obey this. I don't use this word in here often, but this is the proper word I'm supposed to use. They obey the superposition principle, which means that that area would measure a single magnetic field, which is the combination of all magnetic fields that are being created at that point. So it's very unlikely that the red magnetic field is greater in value than the blue. But remember, the creation of the current in this loop isn't about the strength of the magnetic field there, but about how fast that magnetic field is changing. It's possible that that magnetic field is going from a positive direction to a negative direction, but it's the direction of the change that determines the direction of the induced magnetic field. Let me give you an example. There's a problem in your homework where instead of this, we can use the same picture. So I'm going to keep the picture here. But instead of having an expression for the magnetic field, they give you a graph. So I'll get rid of all this. And the graph looks like this. Okay, that'll have to do. And let's say, just to be consistent, let's say into the board is the positive direction. Okay? So I have a function of the magnetic field as a function of time, given to me as a graph. And they give this value and they give this value. So it's linear. You can figure out the slope of that graph, which would be how fast the magnetic field is changing. Now, if you looked at this, this would be a magnetic field that would start out of the page. Right? If I say positive is into the page, this one starts at time 0 with the magnetic field out of the page. And then when the magnetic field begins to change, the magnetic field gets smaller and smaller and smaller. At this moment, the magnetic field is 0 and then begins to grow. But now when it's growing into the page. Everybody follow along with what I just said? The entire time that the magnetic field was changing, a current was induced in that loop that was producing a magnetic field out of the page the entire time. So even though the magnetic field in the little circle started out of the page and changed and went into the page, the induced magnetic field, the one that was created due to the current that was in this loop, the self-induced magnetic field, that one was always out of the page the whole time. Yes, sir?
So the slope went from positive to negative?
The slope stayed the same all the time. The function went from positive to negative, negative to positive.
Well, it's like the slope, or, yeah. I mean, I'm just saying like a separate function where it's more like a parabola where it goes up and then down where the slope is changing. Would that change the current then? Because it goes from a positive slope to a negative slope.
Yeah. That was the example that we had there a moment ago, but our values were positive, so we only had the positive side of the parabola. But if your parabola had a point where it changed direction, then this magnetic field or this current would change direction too. Yes?
So if you recall with that time right there, like time A or something, wouldn't the magnitude be decreasing? So it'd be one direction, and then the magnitude be increasing, so it'd be a different direction?
Okay, so the magnitude of
the magnetic field.
The blue magnetic field?
That's what the graph is.
Yes.
Okay. So like from when it's negative to when it's crossing the axis.
Okay.
Doesn't that mean the strength is decreasing?
Yes.
So wouldn't it be? So that would be one direction, and then wouldn't it, when it's increasing, be a different
No. And here's why. The Faraday's law in this circuit, because right now our flux would just be B times A. Would you agree? Not even dot product, just B times A. Or B pi R1 squared. Is that right? So when we pass it through this function for Faraday's law, we would get equals minus pi R1 squared dB dt. Well, dB dt would just be the slope of this function. Does that make sense?
Yeah.
And that's a constant, and it's positive. But what Adam asked is, what if our function was, this? So if it was parabolic, well, then this slope is always changing. I would probably have a more complicated arrangement here, because now the slope is changing all the time, and therefore whatever current I'm inducing is also changing all the time, and therefore whatever magnetic field that current is creating is also changing all the time. Self-inductance. It's going to become a thing. Self-inductance is where inductors come from. So, I think we have kind of exhausted everything I can possibly say about this circuit. It's got most all the pieces in it. I'd say Lenz's law is the part that I think I want to make sure you understand. Every single problem that has a Faraday's law component is going to have a Lenz's law component as well. And your ability to use Lenz's law is all about determining the direction of the current that's produced, and therefore the possibility for the direction of a secondary magnetic field that's produced. Are we all okay with all that? So, one more thing.